Here we have a proposed reaction mechanism. We're going to assume that this is the overall reaction, and we're going to assume that this happens in two possible steps. What we want to know is which one of those steps is the rate limiting step, or the slow step. So here's our data that we collected from our lab. And the first thing that we're going to notice, so we can get this answer really easily by recognizing that when I change the concentration of B in these trials here, while keeping the concentration of A the same, I notice that my rate doesn't change. That means that my rate does not depend on B. The concentration of B. So right here we can see in this step that if this step was the rate limiting step, it would depend on B. So we can already come up with that fact that this is the fast step and this is the slow step. So I don't really need to do the second part of this, but I will anyways, just to make sure that it makes sense. So if this is the slow step, my rate law should be that my rate is proportional to the concentration of A. So this should be a linear relationship. But we can check that by comparing the ratios of the individual steps. So I'm going to call this initial and this final for the first thing that I'm going to do. So I'm going to say that my rate initial in comparison, or sorry, my rate final in comparison to my rate initial is 0.8 to 0.4. 0.08 to 0.04. Either way, that works out to a doubling of the reaction rate. Looking at the concentration of A final to the concentration of A initial, I can see that that should be A2. I can see that I have 0.4 over 0.2. So I doubled my concentration, and as a result, I doubled my rate. That makes sense for this as a linear relationship. And so if we go back to our rate limiting step and we see our coefficient of 1, this data supports this as a reaction mechanism. We'll do it one more time, looking at this time the first and third trial. Again, my rate final in comparison to my rate initial is 0.12 in comparison to 0.04, or a factor of 3. So if this is linear, then when I divide the concentration of A2 by the concentration of A1, or A final by A initial, I should get 3 as well. And I do, so that again, these two trials also support this as the rate law. So simply looking at the lack of dependence on B, if this overall mechanism is correct, then we can see that since the reaction rate doesn't depend on B, this must be the fast step. Or noticing that A2 in the slow step should lead to a linear dependence. When I double one, I double the other, or when I triple one, I triple the other. This rate law also agrees with the data, suggesting that this is a rate limiting step. So it's not confirmed, but with the information we have here, this reaction mechanism makes sense for this reaction.